Good afternoon and welcome. Our next presenter is Scott Jeschonek. He's with Avere Systems. Please give him a warm welcome.
Thank you, Trish. Yeah, isn't it? It's exciting, and it's pretty loud too, isn't it? All right, cool. So my name's Scott. I'm the director of product management at a company called Avere Systems. We work with a lot of different verticals, media and entertainment. So most of your favorite movies have been using our technology in one way or the other. Life sciences, financial services, anywhere there's analytic workloads that need to be worked on in a high-performance way. And I'm here today to talk to you very quickly about cloud bursting. And I've given you 5 easy steps. And yes, I should have put easy in air quotes, but you'll see what I mean when I get through this. So I'm going to lay the groundwork. I'm going to move briskly through these slides. And then afterwards, if you have any questions, our booth is right up here at 813. Feel free to stop by and ask away. So very quickly, I'm going to define what I mean by cloud bursting and why it's useful. I'm going to talk about some of the drivers, and I'm going to give you some architecture considerations, and then I'm going to walk through an example architecture. For those of you that have the cards in your hand, in the spirit of pure tchotchke, there is a lovely little model dragon that you can win or claim, actually. There it is. She's demonstrating it to you, even though you can't really see it. I could tell you there's $50 bills in there, and you may have to believe it. But just stop back at the booth, and we'll hook you up. Any questions afterwards, like I said, please feel free. So what do I mean by cloud bursting? Very simply, cloud bursting is the act of leveraging cloud compute, such as EC2 or container service, where you have a large number of workload compute nodes that are running processing. And one of the things that you really want to try to do with your compute nodes is get fast access to the data. And one of the big objections that we've heard over the years is some concerns about putting all of your data into the cloud. So you can put it all into S3, you can put it all on EBS volumes, you can even use Elastic File System, as long as your organization is ready from a regulatory perspective, from a psychological perspective, all the human factors of willing to put all of your data into the cloud. If you're already there, that's great. Congratulations. A lot of companies are not, and there's a lot of different reasons for that. And so cloud bursting is, I really want to use the compute power of the cloud without necessarily overcommitting all of my data into the cloud. I may have a lot of expensive servers that I've bought over the years that are still depreciating. Depending on what the tax bill does, maybe they're going to depreciate all at once, but I may not be ready to move everything in. So it gives you the best of both worlds. The challenges that cloud bursting address. First of all, there's this notion of insufficient compute. Those of you that have compute clusters in your data centers, you are already aware of the finite limits of your compute cluster. There's only so much space. You've heard all of these arguments before. I won't belabor them here, only to say that there's never enough compute, especially if you're in life sciences, especially if you're a hedge fund looking for new alpha. It's just you're never going to be able to keep up. Okay, and now I'm going to keep moving from here. But in addition, there's also the consideration of storage bottlenecks. So I have a network-attached storage. I have my HPC cluster. Let's say it's perfectly appropriate, but there's never enough bandwidth. And I will end up with a storage bottleneck if I don't watch myself. And with that, I will have unhappy researchers or analysts hunting me down. So one of the answers that's been there all along, and Amazon has done a great job with EC2 to empower this, is to use cloud compute capacity as an augmentation to your existing on-premise environment. So I may have been working with my compute cluster architecture for the last decade, and I'm not ready to retire it, but I'm also out of capacity and I'm ready to go into the cloud with some of this stuff. So why don't I use my existing queuing mechanism, my existing scheduler functionality, and orchestrate into the cloud some EC2 instances and take advantage of that compute? And furthermore, you all are, I'm sure, familiar by this time with EC2's spot market, so I can also do it in an economical way. But the key for this is I've never really committed my data into the cloud wholeheartedly. Which brings us to the point of data gravity. So it's great that I can use EC2, but the laws of physics are what they are. I can only move the data into the cloud as fast as I can move it across the wire. Furthermore, I will have latency introduced by the software, by the carrier, by any number of issues. It could be game time in US East, for example, and that could also contribute to the latencies. And so how do I deal with latency? How do I make sure that there's enough bandwidth to put all of the data into the cloud? And these things will will conspire to introduce latency as I'm trying to process this job in a reasonable amount of time. So what are my options to overcome this data gravity? Okay, and so first of all, just to be clear, I'm not talking about building a storage archive in the cloud. If you're looking to do long-term archive, I will direct you to S3 and wish you the best of luck. There's nothing wrong with S3 if you have the desire to put data in there and leave it there, and you're not going to look for it in the next 5 minutes, meaning that you're not worrying about eventual consistency. Go for it. There's no problem with that. What I'm talking about is near real-time processing of data in EC2, in ECS. How do I do that? Okay, and I give you 3 options here. This is by no means exhaustive, but these are the ones that we run into in the field all the time. One would be to copy the entire working set. So let's go through that. I have customers today that will copy all of the data for a given whatever job that they're about to work on, and they're going to put that into the cloud, and then they'll run their compute job, and when they're done, they'll terminate all of that. The problem, of course, is that if my job is going to run for days, which some of them may, I'm going to incur the costs of EBS volumes. Most likely I'm going to be using EBS because that's the most direct way of putting it as close to the compute as I can. Also, where will I ultimately store all of that data when I'm done? Do I terminate it? Do I write it back? Do I keep it up there? And then also, locality is of concern. So I copy all the data up to EBS volumes, but I have to have my EC2 instances be able to access that data. And if I've decided to implement a multi-AZ architecture, that becomes problematic for me. Maybe I can use EFS, but the problem with EFS, of course, is at the end of the day, it's 30 cents per gig per month, and it's also it's got performance limitations. So if you're looking for the lowest possible latency, sub 35 millisecond latency that can run tens of thousands of compute cores at one time, that may not be the solution that you're able to rely on. So the second choice would be use object storage, which is, I'm copying the data into S3, and I'm going to do that before I work on it in the data in EC2. And I might use, open source S3FS or something like that to try and get that. But the problem, of course, with that is I still have to get the data there. So I still have the laws of physics. And if I'm a sophisticated programmer and I'm adept with using multi-part puts and all these other things, that's great. But then I have to own that problem, and I have to rewrite my pipeline to make sure that I do own that problem properly. And the other problem, of course, is S3 is eventually consistent. So the data may be available there in the next 5 minutes or in the next day, or 17 hours, or 22 hours. It's variable. And so if I'm trying to copy all the data up with the intent of starting my pipeline right away, S3 is not necessarily going to give you that. You'll be able to list it, but you won't be able to get it necessarily. Okay? So, and then, of course, at the end of the day, it does incur coding costs. I will have to rewrite my application or my my pipeline stack. And so, am I willing to incur those expenses right now today, when I already have a compute environment on-prem and I'm already doing this work on-prem? Which leads me to the last one, data access layer. Yes, I have to confess to you, I am a vendor. And being a vendor, I'm asserting a particular perspective, but that's what this is all about. This is a known working model. You don't have to necessarily use Avere technology to do it, but we have a very effective solution in this spot. And that's where I create a data access layer, basically a performance cache in EC2, adjacent in the same region as the EC2 virtual machines are that I'm about to run the data, and then I point back to my network attached storage that's sitting back in my data center, and I use the advantages of a readahead right behind caching technology to provide near real-time access to that data to my compute clients. And so what are the advantages of doing that? Obviously, I'm going to be reducing cloud latencies. Readahead is a particular technology that says, I am receiving an NFS request for these byte ranges. I'm going to get those, and I'm going to get a little more, because the algorithm, assume that you want more, until such time as you stop asking, and then I will stop asking for more. By doing that, I'm loading only the requested data plus more of the requested data into the near resident caching mechanism that those compute nodes are going to be running. And that is obviously going to give me better performance. And it also is very important to note that it's only going to be putting the byte ranges into the cache that were requested. So I don't have to get the entire file. I don't have to understand multi-part gets to make this happen. It also allows me to do pipeline optimization by being strictly consistent. Whenever you write data to a data access layer, it will acknowledge the clients immediately and then eventually flush the writes back. What that means is if I have a lot of reading and writing in a pipeline, maybe I'm doing transcoding and it's file system based, that's great because the writes are already cached local. So when that read for that write is coming, it's going to be all local up in the cloud instead of having to worry about going back to the network to have storage to get it. And ultimately, by doing this, by only putting in the cache what you need, it's going to reduce your overall storage costs, especially when you think in terms of, let's just say, genomic data, where you're putting terabytes of data potentially in that caching mechanism. You really don't want to store that in the long run in EBS because it'll be quite expensive. And so you only put the data that's necessary in the cache for that job. All right, so now on to the meat of the matter, which is 5 steps to cloud bursting. And you have to love these marketing shows because you all work, I'm assuming, in AWS or some other cloud or technology, so you know there's no such thing as 5 easy steps, but I had to put them in 5. So let's walk through it very quickly. First of all, there are prerequisites to the 5 steps. I need to make sure that I have a good networking environment. The number one problem that we see at Avere with customers is always the network. It's either I have firewall rules that are prohibitive, or I didn't connect my routing tables properly. It's a myriad of problems. Or I'm trying to attach to my on-premise NAS, and the security guys haven't opened up the proper access for NFS, okay? So I need to make sure that all works. I need to make sure that I can reach the EC2 API endpoint, for example. Why do I need that? Because in the Avere technology, we're a clustered solution. So if we have one node fail, we literally go to the API and reprogram the routes so that you can maintain your uptime. And then ultimately, I need to make sure that I have sufficient resources for my HPC cluster, plus my data access layer, which means I need to respect the quota mechanism. I'm sure all of you are intimately aware of working with quotas. So I need to make sure that I have all of the right instances, enough storage space, enough disk space to realize this. I need to make sure that I have a networking component. A 1 gigabits per second link is what we typically recommend, although you can probably go a little bit lower than that depending on the job that you're running. Permissions to be able to access the data in your on-premise environment, and then cloud compute tools for your HPC environment. So people will use something like Univa Grid Engine, which is, has been on-prem for the longest time. Maybe I'm using Star Cluster as an orchestrator, which is perfectly fine as well. That's in your domain to make those selections. It probably has some analog with what you're doing in your data center today. So step 1 is confirming that connectivity. Quite frankly, anything I've ever done on Amazon requires this as step 1. And this is typically where I spend most of my time with customers because there's always some piece along the pipe that was missing, or some firewall rule that was wrong, or the security group is misconfigured, or something along those lines. And for some reason, it's very strange. My background is actually not storage, it's networking. It's very strange how much time you can spend trying to decipher why that security group's not working. I can't quite grasp why it's a little bit strange like that. But this is just making sure everything's working through and through. If you do this up front and you make sure that you can mount endpoints all the way through, you're going to save yourself a tremendous amount of time. The second thing that I typically like to do is get a small instance and create a controller virtual machine up in EC2. This is from where I'm going to launch some libraries. For example, Avere Systems, we publish a setup library in GitHub that you can go and get. Just go to github.com/Avere Systems, and you download that, and that actually makes it very easy to set up the Avere data access layer in basically one command line. But I'd like to do it from a controller VM with a particular permission set, and that guarantees that I'm going to be running it with the right permissions. So I'm going to go from here. The third thing I'm going to do is I'm going to use that library. I'm going to create my data access layer. So this is, in our world, it's basically, I'm going to go to the next slide. This will give you an idea. This is actually the command set. I'm assuming that they share these slides out, so feel free to, if they don't, feel free to stop by the booth and give me your contact information. I can send them to you. But basically, I'm installing Botto. I'm installing our library, which is VFXT. And then I go to the next slide. And yeah, it's a little bit of a longish command, but this one command, which is basically a wrapper script, will set up the entirety of, in this case, a 3-node data access cluster, literally pointing back to an NFS mount point that's sitting on my NAS, sitting in my data center. So once I run this, I'm ready to go from a data perspective because ultimately it's going to be ready to mount that, whatever it's a NetApp or an Isilon or whatever. So then I'm going to basically map the compute to the data access layer. As part of that command that I ran back here, you don't necessarily see it, but it'll tell you in the output that it created a mount point. We call it a vServer. That's your NFS export, and it's basically abstracting whatever's in the back. If it's a NetApp, an Isilon, we even abstract S3 as a file system. And you can present that out the front, and that's your mount point. So basically, I'm going to configure my compute cluster instances to mount that data access layer. Right down here is the command mount with the address and export. If you want to use DNS, we recommend round robin distribution across the cluster. And then once you have all of that set up, you basically run your job. The compute nodes come up. If you have the logic built into your cluster pipeline, you basically automatically mount through etcfs tab is one way to do it, or you can do it manually as part of your script. You mount those data access points, and you run your compute job. And I'm going to back up from here for a second just to show this one grid. And this is what you'll end up with. You'll end up with 1,000 compute nodes sitting in cloud compute, potentially spawn instances, mounting that network-attached storage over your 1 gig link, distributing access across that compute node, compute cluster, and processing the job. And that's the 5 easy steps to running this. I thank you all very much for your time. I refer you to the cards. If you are late to the game here, you can go into our booth, and we have these lovely little dragons that you'll see when you go to our booth. It's like Game of Stones, but we work in media and entertainment, and that's sort of the reference. So I thank you all very much for your time, and please enjoy the rest of this very massive show.